Good morning, everybody. I'm a little slow. I'm just double checking. The connection seems very slow for some unknown reason. So just let me know if you experience any lag or interruptions or anything. We'll see what we can do. All right. Yeah, I'm still waiting for my drawing app to load. I started it. It just decided, nah, not today. Not in the mood. You're on your own. Come on. Things are very slow today. There are signs of life. I see it. Okay, good. Let's see how that goes. So, you had the lovely task to learn about prime numbers yesterday. Now, for the level that we are focused on, it's not a big requirement to get on top of prime numbers. We just want to understand the basics. There is more in the book to explain and prove why there are infinitely many prime numbers, why we know for sure that any number can be broken up into the product of prime numbers, and that is unique, meaning there is only one way. Proving those things for any number, regardless of how large, beyond examples I can make, requires a little bit more. I put it in the book for interest's sake, but we of course do not have to be able to duplicate such things. As I'm speaking, I'm trying to zoom in here. It's just not responding. What is happening today? Let's see if we can at least write. Whoa, it is unhappy today. Wow. Okay, hold on. We have some technical issues here. Severe technical issues are happening. Let me just unplug this writing pad. It's not loving it. This is going to take a while, unfortunately. Sometimes the shortcut buttons just reset themselves randomly, and it goes back to the default setting for no reason whatsoever. Let's see if I can plug and unplug it. Unplug it, plug it back in. See if that works. I know you don't see any of this, but okay, it recognizes it. That's a win. There's just no response whatsoever. There's some response. I'm gonna have to close the collaborate on D2L because that is not adding to our speed here. So let me just do that. My apologies, but looking at the semester, we haven't really had that many technical problems. We've had that one where I accidentally restarted my computer in the morning and it took forever to come back. That was one. That was fun. But apart from that, it really hasn't been bad, I have to say. So let's see here. Yeah, see, I'm on the wrong screen. This is not good. Why? Why? It works every day, but of course now the day I don't test it, I have no other way to write on my screen if it doesn't work. I mean, I can chat, but that doesn't really get the lecture done now, does it? Let's give it a second. It's not happy today. Wow. I just tested it and it was fine. I'll show you here. See, not responding. That's always a good thing. You always want to see that. That instills confidence in what you're doing. Well, we can't really do anything if I can't write. It's kind of silly. Yeah, just end it. Let's close this guy too. Let's try the unplugging method again and reinstall the driver maybe. So how has your week been so far? Might as well fill the air with some interesting chat. Does anyone have anything interesting to say? No, it's just me rambling. All right. Let's do. Let's try and reinstall the driver. Does anyone have any questions about anything you did yesterday? You'd like to chat to make this silence a little bit more enjoyable? Nope, that's nice.
I actually did have a question
Yay,
about
Science of Life. Thank you.
number 5 yesterday.
You're gonna have to tell me what number 5 is because I
Okay,
don't have anything open.
it was asking if number 667 was a prime number.
Oh yeah.
And then so in the video you did the divisibility test going up to 23. And then so you did 23 squared equaled 529. So as soon as we got to there, it was not a prime number, but I just wasn't sure why when we got to 529 that meant we knew that it wasn't a prime number.
Was not. What was the number? 660?
67.
667. So we have to test, and you can do that on your calculator when the number gets a little bit big. Oh, I see the problem here. You have to test divisibility by. Sorry, multitasking is never a good idea. I'm a terrible multitasker.
We can wait then if
No.
that's
You have to test divisibility by all the prime numbers up to a point. What is
right.
that point where you can say, no, I've looked at everything I need to look at? That point, of course, you start with 2, 3, 5, and so on. And the point is the prime number where the square of that prime number is bigger than the number I'm testing. So I have to test, for example, 11, because 11 times itself is 121 and not bigger than my number yet. So I keep going to 13, to 17, and so on until I reach the end of my list. And that's how I know where the end of my list is.
Okay. But so I guess I was just confused because we went to 23 squared was 529. And is it just because we can
So
assume
then
like
what is
we
the
know that
next
the
what is
next
the
one
next prime number after, what was that? 23?
after
That'd be
23?
29, right?
Right. And so we know
So
that that would
29
be too
squared is
high.
way too big, yeah.
Okay.
And then if I've tested everything up to that point, I know that, and they all, none of them divide, for example. Then I know my list that I need to check is complete. And if I haven't found anything from that list, I can conclude with confidence that it is a prime number. So I
Okay.
need to have a complete list, because what if the number that is going to make this result not prime is the very last one in that list? I have to make sure I go to the end and check every one of them. So let's see here. So I check 13. That's, I guess, a no. I can't, if the numbers get past 13, I can't do it quickly in my head. The calculator's totally fine. So after 13, we have 17, and then 19, and then, oh, then 23. So we checked the visibility for all of them, and I'm guessing it was all a no.
Yes. Yeah, it was all a no.
And only then, because I went through my whole list, I can say this is a prime number. I thought you said in the beginning the conclusion was it's not a prime number.
Yeah, I think it was not a prime number.
Well, then one of these have to divide.
23 divides into
Yeah, 23.
650.
Okay, there we go. I'll show it on the chat here. Okay, so 23 divides into 667. So the very last number in my list happens to be the one that throws this whole thing out. And if I don't know to go far enough, as far as I need to go, if I stop at 17, for example, because I get tired and I'm done, I would incorrectly conclude that this is a prime number, when in fact 23 does divide into it, so it's not a prime number. So I need to make sure that I go far enough into and make my list complete. And the way I check that is by multiplying the number by itself. So 23 times 23 is still under my number, so I need to check it. The next prime number would be, like we said, 29. I check 29 squared. I should know these things in my head, but I do not. I don't use it enough. 29 times 29 is 841. Stupid lines. I'm just scribbling now quickly here. 841 is too big, so I don't need to check that one. So my list that I must check to be absolutely certain stops at 23. And it so happens that in some cases, that last guy in my list is the one that throws this out of being prime. And if I don't look all the way to where I need to, I might make the wrong conclusion. So that's sort of what this 667 illustrates, that if I just, and I see many people, they stop at 11 because we only have divisibility tests up to 11. So then I must be done. If I don't find it by the time I get to 11, I guess it's prime. No, you need to check as far as it needs to go, because if the number's bigger, then there are more prime numbers that could play a role here. Just because I don't have the visibility tests for them, that doesn't mean anything. I just stopped because I didn't want things to get too complicated for the divisibility test side. That doesn't really have anything to do with this. So I can use my calculator for when the prime numbers get a little bit bigger, but I do need to check as many as I need to check, because that very last one could be the deciding factor. Factor, get it? Factor? Multiple? No, okay. Does that make a little bit more sense?
Yes, that does. Thank you.
So definitely do not check numbers for which I have divisibility tests only. There could be bigger prime numbers that need to be checked. And sometimes, I'm not always doing it on purpose, this 67 was on purpose. Sometimes only those big ones, one of those might be a factor, not the small ones. Still making it not prime. But I need to make sure my list is complete so that I don't miss those things and I still make the right conclusion. All right, I think we're on track. I think we're back on track here. I have a zoom button, and that's all I really need. Okay. So now we are moving on to chapter, I don't even know my chapter number numbers. What is happening today? 11, chapter 11. So I'm going to put this on the screen. Let's zoom a little bit. Can I zoom? I want to zoom. Allow me to zoom. It doesn't. Oh, there's the plus. All right, so the first thing, before we worry about factors and multiples, is that this prime factorization property of all integers. We saw that previously there's a main result when it comes to prime numbers, that we can factor any integer into some prime numbers, a product of prime numbers being multiplied together to give me my number. So in that sense, then, the prime numbers are the building blocks of all integers, because you give me any random integer, either it is a prime number itself, or it's made up of prime numbers being multiplied together. And for any specific integer, there's only one way. Maybe you can shuffle the prime numbers around, but it's still the same collection of prime numbers making that number. So let's look at exercise 11.1. Now, if the number the number can be big too. It just takes me longer, of course, to find those prime numbers. So we'll pick something maybe in the hundreds and thousands, and nothing too crazy. A nice way to visually as well find which prime numbers make up 100, for example. So I want to know what prime numbers are multiplied together to make 100, because itself is not prime, of course, 10 squared and so on. I can do that by way of a factor tree and say, I'm just going to split my original number up into two numbers multiplied together, and the obvious one is maybe 10 times 10, right? Now for each of these, this 10 is not a prime number, which means it can be split up, and I'm just going to go 2 at a time, 2 and 5. Now 2 is a prime number, and 5 is a prime number, and that ends those paths. Then I'll go to the other number that is at an end, which isn't the prime number yet. This happens to be a 10 again, and I can split that into 2 times 5. And I stop when all my branches end in prime number. And I'll put circles around them so I can easily see them. So that then means that 100 can be written, and the order doesn't matter, but I go in increasing order as 2 times 2 times 5 times 5. Now you can shuffle those around, but still 100 is made up out of 2 2s and 2 5s, regardless of how I write them. Those are the building blocks of this number. You can write them like that, or you can use exponents, which is the representation for repeated multiplication. And I can write 2 squared times, sometimes a dot, if you don't like the time symbol, 5 squared. Either one of them, they're all the same, right? Regardless of how you write them, 100 is made up out of 2 2s and 2 5s. So the factor tree is something that is in the curriculum as well. Oh, don't ask me the grade. These things change depending on the skill of the class. But a later grade, maybe a 5, once they have multiplication down, prime numbers, factor trees, and so on. So it's very useful to me to circle the prime numbers, circle the ends of these branches, so I can quickly see everything I need to list. Okay, so that's one of them. There's no need to make a number too big. Let's do another one, and it is 294. And we'll use these in the upcoming examples. So 294, what prime numbers make that up? So the factor tree is convenient in the sense that I just worry about splitting it up into 2 numbers at a time. And it doesn't really matter which 2 you want to use. So I don't waste a lot of time looking for the 2 numbers to be similar size or anything, just whatever you see. And if all I see is, well, this number is even, so it's going to be 2 times something, if that's all I see, that's fine. Don't spend a lot of time um, trying to come up with bigger numbers or anything. It doesn't matter. Any split of the number into the product of two numbers is fine. So then, maybe to be sure, I'll do a little division. 294 divided by 2 to get the other side of that split. And I get that it is, whoopsie, 147. So now 2 is a prime number. So in this case, my one branch finishes very quickly. Now I have to decide, is 147 prime number as well? Now, in some rare cases, I have to do the full prime number test if by making my list and making sure my list is complete and so on. But I just check my divisibility tests, and usually one of those will catch it. And if none of them do, then yes, I have to make sure. But in this case, I see the sum of the digits, they add up to 12. So this is divisible by 3. And then I just have to find the other number. I can be sure by way of a calculator. This is totally fine. Divided by, 3. And see that the other one is, as you knew, 49. And then it does get easier. 49, I see, oh, okay, it's 7 times 7. Both of those are, of course, prime numbers. And usually we pick numbers that have prime building blocks that are small and familiar numbers. So I can write this in any form I want. I like the exponential form. 2 times 3 times 7 squared. When it's 2 to the power of 1, we usually don't write the 1, but you're welcome to write the 1. So usually there is a smallish prime factor that makes the split fairly easy. In rare situations, it might not happen. So if you can't find a small one, you suspect this is an end of your branch, you want to circle it, then you have to be sure that it is a prime number. So it does happen, but usually we try and get ones that have small numbers involved. So 294 is built on, or built with, a 2, a 3, and 2 sevens, and nothing else. So the idea here is, as we'll see soon, that if I want to understand 294, I can do that by understanding 2, 3, and 7. And whatever properties 2, 3, and 7 have, 294, its properties will be very closely related to that. So the examples that we're going to do later will use these numbers and their prime factorization. Let's keep those two and do the other two on a new page. Like so. So we have 3. Number 3 is 702. So just whatever split I can think of, maybe you just want to use the 2. Maybe I want my tree to be a little bit more balanced. If I pick numbers of similar size, the tree will look a little bit balanced, but it doesn't matter. Right here, I could have said it's 2 times 50 for 100. 2 is an end node, we call it. Then 50 is 2 times 25, and 25 is 5 times 5. So my tree might look different, but I still get 2 2s and 2 5s. It doesn't matter what the tree looks like. It's going to result in the same prime factorization. Your tree might look different than someone else's, but the answer is not. And if you shuffle the 2s and the 5s, it doesn't change the answer. So I'm not too concerned with which split I want to use, as long as it's correct. But maybe I see, oh, it's divisible by 9. Just to keep things a little bit more interesting. I might want to see, well, what is the other factor then? 702 divided by 9. It is 78. And you can always test, is 9 times 78 702? If it is, then your split was correct. So 9 is not quite done. It's a 3 and a 3, of course. Finishing that side. 78. Maybe I only see a 3. And then I'll just show something in the chat to confirm the 3 is a factor of that. 78 divided by 3. And I have 26 left. 3 is done. 26 is almost done. It's 2 times 13. And now both of those are done. And your tree might not look like this. It doesn't matter. In the end, when I sort of sort it nicely in increasing order, I get a 2, I get 3 3s, and I get a 13. Regardless of the tree, that collection of prime numbers are used to build 207. So we have a unique prime factorization, though many trees might get me there. Okay, so that's the first step. Use a factor tree, and of course a quiz question. These are fairly predictable, what the questions will be. It was only part 1 that had some variety. Variety is over. Use a factor tree to find the prime factorization of a given number. So you have to know what a factor tree is, how to use it, and then be able to write your prime factorization. The factor tree is not the prime factorization. It allows you to see the prime factors involved, but you have to write the prime factorization, which is a product of the prime numbers. Many people just do the factor tree and then stop. My question's done. No, it's not. You use that then to write your answer. You haven't technically finished. And because I've now said this, if anyone stops at the factor tree and doesn't write their product of prime numbers, I'm going to have to subtract something, unfortunately. We have one more, 240. So there, it is going to be a touch faster if I balance my tree. It's not important at all. But just to mix things up, maybe I see the obvious 10 times 24. 10 is a 2 and a 5. 24, there are many ways to go here. 4 and 6 maybe. I can't circle those. They're not prime numbers. 4 splits into a 2 and a 2. 6 is a 2 and a 3. And there, every branch is finished in that tree. I have 2 to the power of 4, 3, and 5. That is the answer. Though you get marks for the tree because the question will say, use the factor tree to find the prime factorization. But those two things are technically not the same because someone else could have done trial and error and find the prime factorization. The factor tree is just a nice visual way and a thing that you may be teaching. Students do use the factor tree because it doesn't get much easier than that, and you can focus on little bits at a time and eventually find all the prime numbers. Okay, so we have these 4 numbers that we'll use in upcoming examples. I don't want to go too fast here because we have apparently 2 days scheduled for this, and the amount of material is not worth 2 days, but we don't want to get ahead of our schedule. But that just leaves some question and answer time at the end. If we finish today, then tomorrow, I guess, becomes a Q&A session. But we'll see how far we get. It doesn't have to be like that. The second part of tomorrow, at the very least, will be okay, so now we have 2 things that we want to do with, want to focus on, want to discuss. I'm just looking for my next example here. Where is the next example? Wow. Oh, it's at the bottom here. There we go here. Oh, it's very fitting. So move this up a little. Read it at the bottom here. Example 11.1. You have 24 pieces of Halloween candy and 30 pieces of regular candy to divide equally among some children. What is the largest number of children you can accommodate if both types of candy are to be divided equally? Though I don't know the difference between Halloween candy and regular candy. I thought all candy is Halloween candy, but whatever. You have 24 pieces of one type, 30 pieces of another type, and you want to split them up so that everyone gets the same number of pieces. Okay, so if I sort of go the basic way of analyzing this, I have 24 pieces of Halloween candy. I can give it all to one child, make their day, why not? I can split it among 2 children, and everyone would get the same. I can split it among 3, 4, but not 5, because 5 doesn't divide into 24. 6 children would work, not 7. 8 would work, not 10, 11, 12. And of course, I can split it among 24 kids. Everyone would get 1. So I have a factor list here. List of all factors of 24. Those are the possible number of kids that I could accommodate. But at the same time, I also have to do this for my 30 candy. So for 30, I can accommodate 1, 2, 3, not 4, but 5, 6, not 7, 8, 9, 10. I can accommodate 15 by giving each one 2. And of course, 30 is as far as I can go. So now the question is, I'm looking for the largest number of children. So I'm looking for the largest number in this list that is common to both, and it's a 6. So if I want to split up my Halloween candy and my regular candy in this way, 6 kids is the best I can do. So we call 6 the greatest common factor, for obvious reasons, of 24 and 30. It's a factor of both. It's common to both lists, and it's the biggest one I have. So sort of work backwards. It's a factor, it's common, and it's the biggest, greatest common factor. And for short, because that's a lot of words and letters to write, we write GCF, and then we need to know what were the original numbers, because that determined my factor list and really decides everything. So GCF, greatest common factor, and in brackets, the 2 original numbers. Now you could do it for more than 2 numbers, but there's no real benefit in doing that. Okay, so GCF, greatest common factor. Now, that's perfectly fine at an early elementary school level because my numbers aren't going to be big, and little Timmy can hopefully make a list that is a reasonable size, and it doesn't take him too long to make this list. And once you have the list, great. You just see what's common and how far can I go, what's the biggest one, and you find the 6. Great. But that's a very basic way of doing it, a first step only, because once these numbers get bigger, then my list of factors will get bigger and bigger and bigger. And writing them all out isn't very efficient anymore. It would work if I want to spend the time, but I don't want to anymore once this number gets big, and there's a lot of different factors. It's not just prime factors I'm listing here. I'm listing all factors. So we have to be a little bit more sophisticated, a little bit fancier when the numbers get bigger. Now I'll stick to these numbers because we have an answer for them and we can see in what other way can I get this answer of 6? Well, if I look at a number and want to know how it behaves, instead I can look at what its prime factors are, what its building blocks, and that will essentially tell me how this number behaves. And I can do that for both. So what we can do instead, as an alternative, in preparation for when this list making is inefficient, we can say, well, 24, I want its prime factorization. Well, I'm going to need a factor tree for that. 4 and 6 is one option, ending in 2 and 2 on the 4 side, and 2 and 3 on the 3 side. It's not a big number, so the tree isn't big either. But 24 is built with 3 2s and a 3. On the other hand, 30, I can maybe go 10 and 3. 10, oops, 3 is done. 10 is a 2 and a 5. So 30 rather is built from a 2, a 3, and a 5. So now if I understand what, oops, no, not a D, that's something else. Well, another situation, sometimes called GCD, greatest common divisor, though it hasn't really been used as much recently in my experience than greatest common factor. But I mean, these factors, divisors, technically a factor is a number that divides in without a remainder, whereas a divisor can technically be anything, whether there's a remainder or not. So greatest common factor is a little bit better as a name. But there was a time when greatest common divisor, greatest common factor, they were used interchangeably. Okay, so now if I just understand what these letters mean, I can use the building blocks instead of the numbers themselves to build the answer here. Okay. So now stop me if you don't like this, especially when we get to bigger examples. I'm looking for a factor. I'm going to go right to left here. I'm looking for a factor of 24 and 30, which means I can't go and use a 7, for example, because a 7 doesn't even feature in 24 or 30. It'll never be a factor. Any number that's made up out of prime numbers that do not feature in both cannot be in this, cannot be an answer. So if I'm looking at contenders 2, 3, and 5, those are the only prime numbers that I see. 5 will never be allowed to be in this answer because I need to have a factor of both. It has to be common. So though this 30 is built out of 5s, so 5 could be a factor in here. 24 does not like 5s at all. There is no room for a 5 in here, only 2s and 3s. So 5s are out, but 2s and 3s are in. So let me erase that. So I have to start with the prime factors that I see that are common to both, because the divisibility concept is sort of a fitting in concept. This answer needs to divide into both. This answer needs to fit in to both. And now I look at 24. 24 says, yeah, I'm happy with 2s and 3s. As long as you don't exceed 3 2s, you can fit in. And at the same time, I only have room for 1 3. So as long as you don't exceed that, you'll fit in and be happy. 30 says, I do like 2s and 3s, but I only have room for 1 of each. So even though 23 is happy with more, if you're trying to fit more in, I don't have room. I have room for 1, 2, and that's it. So the 30 and the 24 only allows 1, 3. So that's pretty much settled that. But even though 24 is happy with more 2's, 30 says, no, only 1, can't do more. So I have to, unfortunately, limit my answer that I'm building here with just 1, 2. And that's how we get our 6. Now, once we repeat this a few times, it's going to get better. Don't worry about it. We now want to practice this GCF, greatest common factor. I want to make the biggest one possible, right? The greatest. So I want to use as many prime pieces as I can. But if I'm restricted by 1, then that limits me, unfortunately. All right, so now exercise 11.1, where we're going to use, no, not 11.1 at all. I'm looking at the wrong example. We're going to use the numbers we had previously and find the greatest common factor for some of those. Exercise 11.2. So we're looking for, actually I'm going to leave a space. Leave a space, and then we're looking for the greatest common factor of 100 and 240. So now I have to go and find, where is 100? It was 2 squared, 5 squared. Okay. No. 2 squared. What is wrong with me today? Why am I in a hurry? We have so much time. I need to relax. 100 is 2 squared times 5 squared. 240. Where was that? Over here. 2 to the power of 4, 3, and 5. 2 to the power of 4, 3, and 5. So it doesn't matter that they come from the factor tree. I just need to see their building blocks, and those are the numbers in question here. So now I have to build a factor of each, so it needs to fit into 100, and it needs to fit into 240. Not at the same time, just the requirement comes in 2 parts, which means my answer here has to consist of the building blocks that I see. It needs to fit into both. So it's going to consist of some 2's and some 5's, not 3, because it's not common. Though 240 has some 3's in it, 100 says, no, I'm not linked to 3's at all. I'm not interested. I have no room for them. It's not what I'm about. So I have to start with the prime factors that are common to both. Otherwise, my number won't fit into both. Common. And I'm only using the building blocks that I see because they have to be factors. If I use other prime numbers, they'll simply not fit in the numbers that I'm interested in, because those numbers are made of 2's, 5's, and 3's. Now I just want to make the biggest one possible. So I want to use as many 2's as I can, as many 5's as I can, under the restriction that I have to fit into these numbers. So the largest number of 2's that I can have in my answer is 2. 100 can accommodate up to 2 2's. 240 can accommodate up to 4 2's. I need to be able to fit into both, so the best I can do is 2. 100 says, I'm happy with 2 5's. 240 says, no, I only have space for 1. So for that reason, I have to stop at 1, because I have to accommodate both numbers, trying to make it as big as possible, but I'm sort of stuck a little bit. I like to sort of talk my way through this, build this answer in this way. It shows a much deeper deeper, much better understanding of what makes these numbers tick and what am I trying to do, then you understand what's happening here. Instead of sort of blindly following a formula, use these prime numbers, and if this is bigger than this, and use this, and blah. No, it shows no understanding. I don't want to take a formula approach here. I want to sort of tell the story of how do I make this number. Now, I'm happy if you stop there. I like to see the prime factorization answer, but of course you can calculate it if you want. In this case, it's not big, it's 20. I don't care about the 20. That doesn't show me anything. The detail of the number by way of its prime building blocks, that shows me more. So if you want to calculate it, go ahead, but I don't want to see the 20 and not the detail. 20 is optional, detail is not. I'm going to see the detail. All right. Let's squeeze in the next one, then we can finish. The next one is GCF of 702 and 294. So I want to see what is behind 702. 702. 2, 3 cubed and a 13. 2, 3 cubed and a 13. And 294, regardless of where it comes from, maybe it was given, maybe you had to do the factor tree, regardless, 237 squared. All right, now I have it. So now I want to build my greatest common factor. Okay. Let's do it. Sorry, I missed the YouTube question here. I don't know how long ago it was. I still don't know how to get the videos on Discord, so I can only type. That's okay. I see. Okay, good. Typing is totally fine. I just missed it. I didn't have the window open. Bad teacher. Okay, so I'm trying to build this. So a 2 is a common prime factor, and I'll worry about how many later. I can certainly use 3s in my build because they're common. And anything that has a 3 has a chance of fitting in. But I can't use 13 because 294 is not happy with 13. So it won't fit into both. 7 will fit potentially into 294, but not into 702. So that's as far as I can unfortunately go. Now, with the prime numbers that I have in my answer, I want to have as many of them as possible. 702 says, I only have room for 1, 2, sorry. 294 says the same thing. So 1 is unfortunately as far as we're going to be able to go with the 2s. 702 says, yeah, you can have up to 3 2s. I'm going to be fine if you have that. But 294 says, no, only 1. Only 1. So that's unfortunately limiting me as well. So that's my answer. That is 6 is the greatest, the largest number that can divide into both 702 and 294. I might feel that, no, surely there's a bigger number. No, there isn't. That is the biggest number that can fit into both. We have just a little bit to do today. Let's have a look. Now we've talked about the prime factorization, greatest common factor. There is the other side of that discussion that we'll look at by way of example 113, 11, 11.3, not 113, 11.3. Let's read that. Let me make some space here, like so. Okay. Hot dogs are sold in packages of 10, while hot dog buns are sold in packages of 8. How many should you buy of each so that the number of hot dogs is the same as the number of hot dog buns? Okay. So let's see here. Example. 11.3. So we have hot dogs sold in packages of 10. So that means the hot dogs we're going to get will be multiples of 10. It could be 10. We can have 20 hot dogs. We can have 30, 40, 50, 60, and so on, depending on how much we buy. Hot dog buns are sold in packages of 8. So we'll only ever have 8 or 16 or 24 or 32 or 40 or 48 or 56 and so on. Now we want to know how many should we buy so that the numbers match. So we're looking for the first situation where the numbers are the same, and it'll be this 40. So the best we can have, if we want them to match perfectly, is to have 40 of each. So we're going to call this 40 the least common multiple. It's the lowest value that is common in the two lists of multiples. Least common multiple of 10 and 8. All right. So again, we have these three words, and we write LCM for short, and then simply list the numbers involved in brackets next to that. Least common multiple. So now I'm not looking at factors. I'm looking for multiples of these numbers. So potentially bigger than any of the numbers involved. Common, so it has to be a multiple of both. And I'm looking for the smallest number with that property. So just like we did or observed for the factor list strategy, it's not hard to imagine that if my numbers get bigger, then making these lists are going to be tedious and potentially very long before I find a common one, let alone the first one. So can I exploit how these numbers are built instead to make this least common multiple instead of looking it up in a list? While my numbers are small, I can make sure to give little Timmy small numbers in the beginning, so he's going to find it without having to make a long list. It's good practice, definitely in the beginning. But if I let these numbers get even remotely big, this is just not a good enough strategy. It's not efficient anymore. So let's have a look. My numbers aren't big, so finding their prime factorization should not be a problem. 10 is simply going to be 2 times 5. 8 is simply going to be 2 to the power of 3. So now, when I want to make this least common multiple, it's sort of a reverse situation. That I'm not going to try and make something that fits in to each of the numbers. I want each of my numbers to fit into what I'm making, the multiple. Now I think of a multiple as being bigger and each of them fit in, but it could be the number itself in some cases, right? Let me just double check the YouTube chat here. I don't have it open. Maybe someone has a question. You never know. Forgot to open it. Okay, seems good so far. Okay, so if I want 10 and 8 to fit into my least common multiple, I'm going to have to make sure that I see the building blocks that they use. So I'm going to have to see a 2 and a 5. 10 says, yeah, if you see 1, 2 and 1, 5, I'm going to fit. All my pieces are there, so I'm good. 8 says, yeah, I don't care much about 5. Do whatever you want. Have more in there. But I need to see 3 2s before I can fit in there. So right now, I'm not able to fit. You need to up that number of 2s to 3. 10 doesn't care how many 2s you have. It just needs to see one of them. But I need to up the number of 2s to make 8 happy. Now 10 can fit into that because I see its pieces and the correct number of them. And 8 can fit in there as well because I see its pieces and the correct number. Now I don't care what the answer is. I care about how to make it. Any monkey can calculate that on a calculator. So I have a multiple. It's a multiple of both, and it's the smallest I can make it. I can't go any lower on the number of 2s, and I can't go any lower on the number of 5s. So that is the best situation. All right. So now we're back to our, let me open the book here. We're back to our examples that we have over here, where we want to use the prime factorization instead of making lists to find what makes, how to make the least common multiple of these guys. So we are over here somewhere. There we go. Exercise 11.3. So while I am writing it down, you have to tell me what the prime factorizations were, because I don't have my notes of yesterday. And though it could be fun to do the whole factor tree again, we have done it. We can just go and look what the prime factorizations were. So I'll put them side by side. So first up will be 100 and 240. Now 100, correct me if I'm wrong, was 2 squared and 5 squared. But I don't remember what 240 was without having to do the tree. So can someone look it up and tell me what it was? As a side test to see if you were paying attention. 240.
It was 2 to the power of 4 times 3 times 5.
All right. I didn't want to guess and remember wrong. Perfect. Now, of course, we need that just like we did for the previous one, right? Whether that's given to you, sometimes I just give it to you and ask a separate question for the factor tree, or whether it's part of one big question where you have to do the factor tree first and then use that answer for the next step. Regardless, we need this. So now I am going to make the least common multiple of these two. Okay, so it's not the same as the greatest common factor, because factor and multiple, they're different concepts. So I need to make sure that both of my numbers fit into what I'm making here. For 100 to fit, I need to see some 2s and I need to see some 5s. I'll worry about how many in a second. For 240 to fit, I need to see 2s, 3s, and 5s. So at the very least, all the prime factors that I see among all of these need to be present in my least common multiple. Now it's a question of how many. 100 says, I'm happy with 2 2s. 240 says, no, I need 4. So I'm going to have to go to the higher number of 4s because I need to have it common. And the best I can do, while still making each one happy as far as the 2s go, is 4. 100 says, I don't care about 3s, do whatever you want. 240 says, I just need 1 3. Okay, so 1 is enough. 100 says, I need 2 5s. 240 says, just 1's fine for me. So the smallest number of 5s I can get away with is 2. And I'm done. Calculate that, don't calculate it, I could not care less. But if you calculate it, then just make sure you are correct, of course. You're welcome to stop right there. Because it's more important, the understanding is more important. Anyone can punch that into a calculator and get that number. That number means nothing to me. But looking at its building blocks, that means way more. So as long as I can distinguish between what greatest common factor means and what least common multiple means, keep those two things separate, then and understand what each one requires, then I just take from the prime factors what I need. Number 2, 702 and 294. Do the factor tree again if you want to, but because we have done it, I see no need to do the same thing again. Can someone tell me the prime factorization of 702? You don't have to do it, just go look it up. You should have it in your notes. Or someone. Not everyone takes notes because the video's there.
2 times 3 cubed times 13.
All right, and then 294.
2 times 3 times 7 squared.
2 times 3 times 7 squared. That looks familiar. Okay. Now, we want to make the least common multiple, 702 and 294. That's an equal sign. So, I need to see all the prime factors. Not caring that much about how many right now. I need to see everything that I see among the numbers. 702 needs to have a 2, a 3, and a 13. So I need them. 294 needs 2, 3, and 7. So I need to see them. Now it's a question of how many. When it comes to the 2s, both of them are happy with just 1 2. Now they don't have to fit in at the same time, so I don't need to make space for both to fit. Just 702 needs to fit, period. 294 needs to fit, period. So I just need 1 2, and then both of them will be happy. 702 needs 3 3s, when 294 only needs 1, so the best I can get away with is 3. Otherwise the 702 won't fit. 702 doesn't care about 7. 294 does and needs 2. 702 cares about 13, only needs 1. Now you can write the 1 there if you want to. But if it's a 1, we all come to the agreement that you don't have to write it. And 294 doesn't care about 13s. And there I'm done. Now just to contrast this with the greatest common factor, without looking, I'll do, well, I don't have the choice, I can't look. I'll do the greatest common factor again to see how these compare. For the greatest common factor, I'm trying to make something that fits into these numbers. So it's very much the reverse situation. So I'm only going to look for prime factors that are common, because this that I'm constructing here needs to fit into both. So a 13 won't fit into the second number. Having a 7 will cause it to not fit into the first. So it's only the ones that are common. I want to make it as big as possible, but if I have more 2's, it won't fit in anywhere. So 1 2 is all I can do. And if those 702 will be happy with many 3's, 294 won't. So I won't be able to fit if I up the number of 3's to more than 1. And that's it. So it's different. I would suggest aim for understanding more than just memorizing. Oh, take all of them, then look for the highest number, highest exponent every time, and sort of shut down your thinking and just go through the motions. That can be dangerous. I don't like that approach. Understanding beats memorization almost always.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.